everyone. Thank you so much for your patience today. We have some really exciting speakers lined up. We thank you so much to all of our presenters, our speakers, for taking time out of your busy schedule to share your experiences and knowledge with us. And without further ado, let me introduce Hakeem. Hakeem, how do you say your last name? Sorry.
Balogun.
Balogun. Yes.
Hmm.
Hakeem holds a bachelor's degree in aerospace engineering and a master's degree in mechanical engineering from Tuskegee University. Hakeem served as an aerospace structures engineer at NAV Air from 2015 to 2020. Hakeem is currently a first year aerospace engineering PhD student at Auburn University. His research primarily focuses on topics in experimental aerodynamics. These include the study of delta wings, vortex dynamics, and thrust vectoring utilizing measurement techniques such as particle tracking. Ooh, the Hakeem, help me out with that word.
Particle tracking velocimetry.
Woo, okay, so I'm really excited to see your presentation and found out more about this because this is definitely not my area of expertise. So, Hakeem, take it away. I'll let you present your slides.
Okay, just some background about what we're talking about. So, delta wings are a planform shape commonly used for fighter, bomber, and UAV craft. And this shape produces lift at high angles of attack due to the creation of leading edge vortices that shed from the leading edge. These vortices produce lift at angles of attack that typically cause stall conditions over other planform shapes, and delta wing configurations are highly maneuverable and provide structural benefits compared with typical aircraft design. And these leading edge vortices are shown on the left hand picture, and they kind of shed off from the body of the aircraft. So, next slide, please. In order to really talk about leading edge vortices, I need to describe some of the vortex topology. So, if you look at the top left image, um, what it shows is that delta wings produce leading edge vortices along the section side of the wing. And these vortices are formed by a characteristic shear layer rollup along the leading edges of the delta wings. And as these shear layers curl, they produce strong counter rotating jet like vortices. Something also to note is that the primary vortex structure that we see on the delta wing originates as a series of smaller vortices shed from the leading edge that travel parallel to it. And then that curls into that concentrated counter rotating jet like vortex that we normally see. Instabilities in the shear layer lead to a phenomenon known as vortex burst. And this is shown on the image directly below, where a vortex burst is a sudden breakdown in the coherent vortex structure. And there are typically two main types of vortex breakdown: bubble and spiral type. So in the bottom left image, we're seeing the bubble type breakdown. And what happens is that along the axis of the vortex, there is there are instabilities that cause a sudden expansion of the vortex, and that leads to a viscous weight right directly behind it. The two images on the right, they're showing crossflow slices of leading edge vortices that were imaged using laser smoke, laser flow smoke visualizations. And the top right shows the leading edge vortices without breakdown, and the bottom right shows the port side vortex breaking down, and that's kind of evidenced by the diffused areas of smoke. We can go to the next slide. To describe vortex breakdown some more, if you look at the top right, the top left image, this is showing the bubble type breakdown. So for both types of breakdown, the spiral and the bubble type, they are a result of adverse pressure gradients along the axial direction of the vortices. And this creates a region in the vortex core where the flow begins to stall. So for bubble type breakdown, flow stagnation creates a region where fluid lumps together in an ovular shape in the axial direction of the vortex core. And for spiral type breakdown, which is the two images directly below the bubble type breakdown, um, that results from flow stagnation in the axial direction along the vortex core, leading to flow acceleration in the azimuthal direction. And this creates a kink in the linear vortex core, forming a helix shape that spirals 2 to 3 times before turning into a turbulent wake. So now I'll discuss trailing edge jets, also known as stress vectoring. So because vortex breakdown is characteristic of leading edge vortices produced from delta wings, there have been quite a few active flow control techniques to delay and mitigate the adverse effects of vortex breakdown. One such method is thrust vectoring, and that's just a directional vectoring of jet exhaust. So thrust vectoring is important for aircraft that want to maintain air superiority and maneuverability. They also help with maintaining lift and altitude as the flow over fighter jet wings stall. So if you look at the two images on the right-hand side of this slide, you'll see for the top right image, this is showing die flow visualization of the leading edge vortices on the delta wing. This is without jets or thrust vectoring enabled. And the image right below it shows the exact same situation, just with thrust vectoring on. So what's essentially going on is that thrust vectoring has been shown to be effective in mitigating vortex breakdown, um, such that the vortex axis extends, and in some cases can extend past the trailing edge of the delta wing. And this is caused by the jet entrainment effect, where the low pressure region and the vortices produced by the jet exhaust entrain with the vortices produced from the leading edge of the delta wings. And this helps to reduce the pressure gradient increase caused by flow stagnation that's characteristic of vortex breakdown. And this is important because vortex breakdown causes dynamic and static stability issues such as wing rocking, which are limit cycle oscillations of the delta wing along its roll axis. So if you've ever seen an airplane rocks, the wings rock side to side, that is a result of wing rocking, and that's typically caused by the vortex breakdown on like these delta wing type fighter jet flying wing configurations. So I want to talk about vortex breakdown detection and quantification. So typically, the two slides I showed, the slide I showed before was a die flow visualization. That's what we call a qualitative experiment. So for the purpose of my experimentation, I wanted to do qualitative and quantitative experimentation. So in order to do that, I'm using a vortex identification method called Q criterion. And that simply defines vortices as regions where the vorticity magnitude is greater than the magnitude rate of strain. And for this particular schema, detection of vortices and vortex breakdown in PIV data, and PIV stands for particle image velocimetry, can be performed using this analysis method. It's a decomposition of the velocity gradient tensor, and it's one of the most widely used methods for vortex identification. There are a couple others like lambda chi, lambda 2 identification criteria. But Q criterion, like I said, works by decomposing the velocity gradient tensor into its symmetric and anti-symmetric parts. And the symmetric part is the strain rate tensor. The anti-symmetric part is the vorticity tensor. And you solve for the three invariants of this tensor. Q is the second invariant of this velocity gradient tensor. And in PIV data, positive values of Q criterion indicate vortices or vortical structures in the flow. This is important because what it's really telling us is that a vortex can be considered as a region where the vorticity magnitude dominates or is greater than the magnitude rate of strain. And essentially, Q is measuring the difference between these two, the rate of rotation and the rate of strain. So for my experimental setup, the top image shows our experimental setup. This is, my qualitative dye flow visualization and my quantitative PIV experiments were done in the open surface water tunnel at Tuskegee University. For the PIV system, we have the TSI V3V Flex Volumetric PIV system. It has 4 25 megapixel CCD cameras to capture images. Each camera offers a 5120 by 5120 pixel resolution with a 4.5 micrometer pixel size. A Quantel Evergreen dual pulse 200 megajoule laser is utilized for flow illumination, and the optimized measurement volume is 200 by 200 by 100 millimeters cubed, with 100 millimeters being the depth from the plane of the cameras into the water tunnel. So really, just to explain a little bit, what PIV does is we add these microscopic or even nanoscopic tracer particles into the flow field, and we use high-speed cameras and lasers that when the lasers shine, the particles in the flow, they refract and reflect some of the light, and the cameras are able to take images of the flow field in sequential order, and from there, we're able to reconstruct the flow field. So for my experiments, I used a non-slender delta wing, and it had a 50-degree sweep. You measure the sweep angle from the nose to one of the leading edges. For non-slender wings, that means the sweep angle is less than 65 degrees. For slender delta wings, that means it's greater than it's 65 degrees and greater. The root chord of the delta wing was 114 millimeters, and the model is 3.175 millimeters thick. And I put a 30-degree leading edge bevel on the suction side of the wing. The nozzles that simulate thrust vectoring are angled up 20 degrees relative to the root chord, and the nozzle exit diameters are approximately 3.175 millimeters. I generated or simulated the thrust vectoring for this experiment using one 12-volt DC water pump on each nozzle inlet, connected using Tygon plastic tubing. And that's shown on the image directly below the schematic of the delta wings. I have the tubing going into the inlet of the delta wing. I have a dye probe there in order to visualize the vortices for qualitative experiments. And from there, the pumps have a maximum flow rate of 0.233 millimeters cubed. And these models, or this model was printed using the Formlabs 3 Plus 3D printer. And that printer is great for producing aerodynamically smooth models. So thank you. Next slide, please. So for data analysis, for the non-slender delta wing, the Reynolds number was 22,000. And I took data at angles of attack of 15 degrees and 25 degrees for certain jet velocity ratios. So the jet velocity ratio is simply the ratio of the jet exhaust velocity to the free stream velocity. And I modeled this off of real life jets, specifically the F119 Pratt & Whitney 100 turbofan engine, and the takeoff speed of the F-22A Raptor, which is 241 feet per second. And the jet exhaust velocity of the Pratt & Whitney engine, turbofan engine, is 2,985 feet per second. So I got the maximum jet velocity ratio, and I scaled it down for the purposes of our experiment. So now I'll go into some results of dye flow visualization. So the image on the far left, it shows the chord stations that I marked on the delta wing. So I'm trying to quantify vortex breakdown for the qualitative experiments. So the black lines just represent chord stations from the root chord stations from the tip of the nose to the trailing edge, and they're denoted from 0 to 1. So for a chord station of 0.6, that means you're at 60% of the chord measured from the tip of the nose And for like a chord station of 0.3, that simply just means you're 30% of the way from the nose. So for the diflow visualization, for a 15-degree delta wing, this is the image in the middle. The average root chord breakdown location was approximately 0.5 or 50% of the chord without trailing edge jets. And with the introduction of trailing edge jets, the vortex breakdown location didn't noticeably change, but I noticed in my data that the rate of rotation about the vortex axis increased with the introduction of trailing edge jets. So this is showing that the jet entrainment effect is still in effect, even though the vortex breakdown location might not move further back for this particular angle of attack. And this is important for the PIV data that I'll show later. For an angle of attack of 25 degrees, the root chord breakdown station was 0.15 or 15% of the chord. And with the introduction of trailing edge jets, this location extended to approximately 0.18 or 18% of the chord, and would shift back and forth to about 0.2 or about 20% of the chord. And this is the image on the far right side. And also, I noticed for this diflow visualization that the rate of rotation about the vortex axis also increases with the introduction of trailing edge jets. So for the 15-degree case, we didn't get noticeable change in the vortex breakdown location, but we did notice that the vortices were being influenced by the jets. But for the 25-degree case, we saw more evidence of the vortex breakdown location moving further down the chord. And we also noticed the rate of rotation about the vortex axes of the breakdown of the broken down structure increasing as well. Next slide. So now I'll get into the results of my PIV data. So this is for the 15-degree angle of attack case with a Reynolds number of 22,000. And so diflow visualization for this configuration showed that the mean breakdown location was approximately 0.5 without trailing edge jets. Something to note, at this angle of attack, the vortices form really close to the suction side of the delta wing. And after the breakdown area, the diffused vortical structures continue to swirl along their respective axes. And this movement is pronounced and was readily visualized with the diflow data. So looking at the PIV data, on the far left, I have the root chord breakdown stations, root chord vortex breakdown stations, and they go from 0.4 to 0.7. So from 40% of the chord to 70% of the chord. And when you go right, I have increasing values of the jet velocity ratio. So I'll start from the far left. So at a jet velocity ratio of 0, meaning jets off, the vortices spread out horizontally. The vortices spread out horizontally as one travels from a breakdown location of 0.4 to 0.7. So in the first column, as you go down, the vortices tend to spread out. And this is a consequence of the breakdown. This is a consequence of the development of the vortices as they go down the chord, and as they break down, the influence of trailing edge jets is pretty pronounced for this. So for instance, at X over CR 0.6, the for jet velocity ratio of 0, the vortical structures show signs of expansion, and that's evidenced by the reduction in the values of Q criterion at X over CR 0.6 and a jet velocity ratio of 0. And by X over CR 0.7 or a root chord station of 0.7, the residual vortical structures have almost completely diffused into the flow field. And with the introduction of trailing edge jets into the flow at X over CR equal to 0.5, the two primary vortical structures change from a sort of ovular or semicircular shape to smaller, more elongated vortical structures. So if you come to where it says UR equal to 1.236 to 12.36, as we increase that jet velocity ratio, the vortical structures tend to elongate and get smaller. And this is reminiscent of the shear layer curling around the axis, which is something I mentioned about the die flow visualization. So the PIV data is revealing quite a bit about the flow that wouldn't normally be known just through die flow visualization. So these vortices, they grow smaller as we increase the jet velocity ratio, and the introduction of trailing edge jets are helping to mitigate this expansion of the shear layer as a result of vortex breakdown. So at x over CR equal to 0.6, for the cases where the jet velocity, for the cases where the jets are on, the primary vortical structures become smaller. And as you go from x over CR 0.6 to, 0.5 to 0.6, the vortical structures become smaller as you increase the jet velocity ratio, with the starboard side vortex almost disappearing at a jet velocity ratio of 8.65 and 12.36. And again, so what is going on is that as I increase the jet velocity ratio, the jet entrainment effect is more pronounced. So this causes a higher rate of rotation about the vortex axis. So for the purposes of PIV data, this causes the vortical structures to interact with the surface of the delta wing, especially at a 15-degree angle of attack, where the delta wings form close to the surface of the wing. And through some boundary layer interactions and the increased rate of rotation, this causes the vortical structures to appear smaller in the PIV data. And for the starboard side vortex, this is really pronounced for the starboard side vortex as you increase the jet velocity ratio. That's the right vortex in these pictures. And what's interesting is that this is really pronounced because the models were painted black for the collection of the data. And because the black color absorbs the light, it gets kind of difficult to really image the vortices near the surface of the delta wing. But that's something for future work. But go to the next slide, please. So I'm showing more results of the data for an angle of attack of 25 degrees. And die flow visualization for this configuration, again, showed that the breakdown location was approximately 0.15 or 15% of the chord to approximately 0.18 to 20% of the chord. And for this configuration, very large wake-like structures that span the entire starboard and port sides of the delta wings were noted in the die flow visualization. So one thing that's interesting about this data is that the vortical structures are a lot larger than they were in the previous slides. And that's mainly because the vortices have lifted off noticeably from the surface of the suction side of the delta wing when compared with an angle of attack of 15 degrees. And you can tell really by the shape of the vortices. And in the previous slides, again, for the 15-degree angle of attack, the vortices were really being impeded by the surface of the delta wing. So if we're looking at this data, we start at a breakdown location of 0.2 when the jet velocity ratio is 0. The two vortex structures are present in the PIV data. And by adding trailing edge jets into the flow, so if you start from 0.2 and go all the way to the right, you notice that the size of the vortical structures reduce when compared with the baseline case being jets are off. And when you go further down the chord to a breakdown location of 0.3 and 0.4, the primary vortical structures begin to expand in size as the structures diffuse into the flow field, which is characteristic of vortex breakdown, where the sudden expansion of the vortices on the delta wing cause them to diffuse further into the flow field. Now, if you look at the introduction of trailing edge jets into the flow, the trailing edge jets mitigate the expansion and diffusion of the vortical structures. And this is shown by the vortices generally reducing in size at a breakdown location of 0.3 and 0.4 as we increase the jet velocity ratio going to the right. Also, what's interesting is that at high levels of Q, there are high levels of Q criterion that are present all the way up to X over CR 0.5 for all of the UR cases examined in this data. And what this really shows is that after the physical indications of vortex breakdown, like what I used for the dye flow visualization, that this sudden expansion of the vortex core still results in relatively high levels of residual vorticity in the flow field. And these show up as semi-coherent vortical structures. And again, this was corroborated by the dye flow visualization data. And with the introduction of trailing edge jets into the flow, these vortical structures at X over CR 0.5 gain strength as evidenced by the growth of the red contours of Q criterion relative to the portion when the jets are off at UR equal to 0. As you go to the right, we see that the red portions of the plot increase in size more, indicating that the vorticity magnitude is increasing relative to the rate of strain magnitude. And this is just another indication that the increase in vorticity magnitude is due to the jet entrainment effect and is especially enhanced as we increase the jet velocity ratio more and more. And as we go further down the core to X over CR 0.6 and 0.7, the vortical structures, when the jets are off, have really irregular shapes, and they've almost diffused completely into the flow field. But as we turn our jets on and increase the jet velocity ratio going to the right, we see increases in Q criterion, which again indicate that the vorticity magnitude is increasing relative to the magnitude of rate of strain. So just some conclusions. Particle image velocimetry data can reveal residual vortical structures in the flow field, despite physical indications of vortex breakdown that you might see from dye flow visualization or smoke flow visualization or any type of flow visualization that you might use. And that trailing edge jets reduce shear layer expansion because of vortex breakdown. Trailing edge jets also can influence the flow field despite vortex breakdown being pronounced, especially near the nose of the airplane or the delta wing. And for future work, this is stuff I'll be doing for my PhD. I want to manufacture near transparent models for near surface suction and pressure side investigation of the vortical structures. I want to perform comparison studies using different trailing edge jet cross-sectional shapes like rectangular and triangular, and at different jet angles relative to the root chord. So maybe 30 degrees, 40 degrees, where I'll angle the jets up relatively higher and higher. And I want to investigate the effects of trailing edge jets on delta wing instabilities, such as wing rocking and wing dropping. And that is it for my presentation.
Okay, thank you so much, Hakeem. That was very, very interesting. We really appreciate you